So this week we'll have a face-to-face meeting in the lab. Okay. So later today I will release the lab punya splitting, who goes into which particular lab session, and we will also be having a quiz at the end of this week later on. Okay. All right. Having said that, now this is the what we call the task structure, basically to represent our our okay, to present our to model, basically to model our system. So there is some terminologies that you guys need to understand. Okay. So basically, oops. If we talk about periodic tasks, periodic tasks mean things that happens at a certain period. For example, if we do something every 5 seconds, so that's something we call it a task. Okay. That something can be reading data from your sensor or activating your whatever actuators that manipulate your system. Okay. And every iteration of that task, we call it a job. Okay. The task itself, we call it a task. Okay. And for example, the task is to read data from sensor A at every 5 seconds. So that is a task. But every time the task execute at every 5 seconds, we call that a job. Okay, job number 1 of task number 1, job number 2 of task number 1, job number 3 of task number 1, meaning job number 3 will be at the 15 second, job number 2 will be at the 10 second, and job number 1 of task number 1 will be at 0 second when the system starts. Okay, every 5 seconds. Sorry, at 5 seconds, not 0. All right. Now, a job J sub I, we denote job J sub I by our notation is J sub I. We execute for the time. This is the execution time. So what is meant by execution time is, for example, if our period is 5 seconds, okay, let's say we start executing the task from time 0. All right, we execute it. Let's say it runs up to here. Maybe here is only 2 seconds. So this is the amount of time that that particular job spent, which is its execution time. Okay, this is the execution time, denoted by E sub I. I means the first job, second, I equal to 1, equal to 2, and so on. Okay. Any questions so far? Simple, right? Now, value of E sub I depends upon complexity of the job and speed of the processor on which it is scheduled. Now, to understand execution time, let's say you write a piece of code to do something. Okay, you write a function, void, blah, open curly bracket and close curly bracket in C. So whatever you did inside here, from the point in time it starts here until the end, now that is the execution time. Okay, if this particular function represents your task. Well, if it happens that your task is represented in a single program, then the whole program is denoted as its execution time. Okay, execution time falls in the interval of E sub I plus and E sub I minus. Assume that we know this interval for every hard real-time job, but not necessarily the actual E sub I. Now, why is that we have plus and minuses? Why can't E sub I be fixed? Any guess from your side? Why can't we have a fixed E sub I? Well, the notes tells you already. Okay, depends upon the complexity of the job and speed of the processor. Well, of course, that will contribute to the amount of execution time. But why is the fluctuation pluses and minuses? Any guess? Okay, when you write your code, you use if else, right? You use looping. In assembly, you have branching, jump to here, jump to there. Now, it's possible in the first time you execute it, it uses a different else punya instruction. Let's say if inside your if else to you ada if blah, then you do this. Else blah, then you do this, right? Now, if first time the job runs, it executes this one, and second time it runs, it executes this one. Of course, there is a high potential that the execution time will vary, right? From the first to the second, but it won't vary much depending on what you do inside the if else. So there is plus and minuses. And then here it says, often we can validate a system using E sub I plus for each job. We assume E sub I is the higher bound, E sub I plus, not the lower bound. And ignore the interval lower bound. What's your understanding about this? Why do we take E sub I plus, not E sub I minus, as the execution time? Hello? Anyone has any idea? Kenapa kita ambil E sub I plus, not E sub I minus? This is the maximum execution time, no, we say. Okay, E sub I plus is the maximum execution time. Or technically, we call them worst case execution time. Why? In the case of real-time system, now think about this, right? Again, your car braking example, right? By means of testing, that won't be very logical. Let's take the example of the pilot. Okay, I think in last lecture, last discussion, I did introduce you guys the fighter pilot jet. Okay, once the jet is being shot, so what the pilot will do is to eject himself from the fighter jet so that he's alive, right? He's safe, right? Now, the point in time when he pressed that button, let's say the system must respond within 5 milliseconds. Okay, that is the E sub I. However, like we said, there will be E sub I minus and E sub I plus, right? Let's say the E sub I plus is plus 1 millisecond, which is 6 milliseconds. Okay, the E sub I minus is 4 milliseconds. So the safe bound is E sub I plus. We take E sub I equal to 6, not E sub I equal to 4. Now, why do we do that? Why don't we take E sub I equal to 4? Because generally, there is a law that says something because it's a safety measure. Something that can goes wrong, it will always go wrong. Murphy's law states that, right? I mean, if I take the larger execution time, I mean, definitely it will happen. Maybe it doesn't happen all the time. I mean, maximum execution time. Let's say if you run the same job for 100 times, maybe the maximum execution time only happen once. But if it happens, then your system must be designed to cater that so that the whole system work without failure. It cannot be that your system is designed to only work when E sub I equal to 5. And then when worst case execution time happens, your system fails. So in real-time system, we must design the system to meet the worst case execution time. In other words, in all cases, your system must work without failure. This is, of course, talking about hard real-time system. Okay. Any questions so far? Look at the comment below here. Inefficient but safe bound. Why do we say that? Taking E sub I plus is inefficient.
Because it takes the maximum amount of time.
And that maximum may not happen all the time. Again, most of the time it will be, let's say, 5. Maximum will happen maybe once or twice only. Right? This might happen once or twice. This will happen maybe 99% of the time. And then minimum also E sub I minus will happen maybe 1% of the time. Okay, but if this happens, it must be handled safely. Okay, that's why we say it's inefficient. But in real-time system, our main concern is the safety of the system. If you remember by the definition in our first lecture, what is a real-time system? A system that if it fails, then we are talking about loss of life, huge amount of loss of money. Means something catastrophic, something very severe will happen if your system fails. So those kind of system, those kind of computing system is classified as hard real-time system, meaning meeting the deadline given is very, very important. We don't concern about efficiency here. Our main concern is to be safe. Even though we lost a bit 99% of the time, our system might be a bit late, for example, right? But still, it is safe. Now, that is different for general purpose computing system, like our discussion in previous semester in modern operating system. In modern operating system, we won't take E sub I plus, we will take E sub I only, because our main concern is efficiency. In ordinary computing system, like my laptop, right? For example, if I press the start button 100 times, it fails once. Well, that's okay. Or maybe in 1,000 times, it fails once. I can always repress the start button without any problem, without any harm happening to me or without any harm happening to the laptop. So those are considered as general purpose. So our main concern is efficiency. But for real-time system, because the failure of a real-time system will be very catastrophic, will be very severe on human, on money or things that we care about, then we define those as real-time system. And we need to design for worst case scenario. Okay, so remember that we're using E sub I plus. All right, what about release and response time? What is release and what is response time? Release time, the instant in time when a job becomes available for execution. Okay, the release time is the instant in time when a job becomes available for execution. What about response time? The length of time from the release time of the job to the time instant when it completes. If you remember our modern operating system class, you remember our Mickey Mouse, right? We have one bubble here, one bubble here, one bubble here, one bubble here, and one bubble here. So this is the new state. This is the ready state. Okay. This is the running state. So this is the exit state, and this is the block state, right? It can be like this. So things are related. What we learned last semester and this semester. All right. So it says release time is the incident time when a job becomes available for execution, which is here. When the jobs are in ready state, means they are ready for execution. They are just waiting for the scheduler to select them to run. Okay. So same case here. What about response time? The length of time, the amount of time from the time, the release time from here of the job to the time instant when it runs. Okay, when it runs, it gets selected here. Well, there are many things can happen. It can go here, and after that, of course, it goes back here, or it can go here, and finally it goes exit. So all in until it goes to exit, that is the response time. How long your job? Okay, not the same as execution time. Why is not the same? Do you see the difference? Execution time differs from response time. What's the difference here? So based on this bubble, where is execution time? Where is execution time? It's here. This is execution time. When it sits on the CPU, using the CPU time to execute. Okay. However, response times involves 1, 2, 3. Also, the time it was blocked for I/O, blocked for whatever reason. Okay. So response times includes blocking time, the time the jobs was blocked. Okay. Any question? Don't be confused with this figure right here. All right. It shows it runs to the end when it finishes. Looks like it runs without stopping, meaning from ready, it goes to running, and then immediately it finishes. The job was lucky. It doesn't get blocked. It doesn't have any I/O instruction inside. Okay. But what is meant by response time in actual is, of course, all in until it finishes. From the point it starts running, it gets selected to use the CPU until it runs to completion. Ada soalan? Tak ada. Now, deadline and timing constraint. Okay, we have completion time. You guys need to be able to differentiate all this. All right. Relative deadline, absolute deadline. Okay. And then we have feasible interval. All right. Completion time, the instant at which a job completes execution. Right here. Pukul berapa? What time it finishes? It finishes at 11 a.m., for example, right? Now, relative deadline, the maximum allowable response time of a job. In other words, the amount of time. How long? Okay. Usually, we always assume the period equal to relative deadline. So in the earlier example, when I say 5 seconds is the period, in that case, the deadline is also 5 seconds. So we always assume that, unless mentioned otherwise in any specific case later on. All right. So this is the relative deadline. What about absolute deadline? It's the instant of time. Pukul berapa juga. Same like completion time. What time it is the is the deadline of a particular job. Now, let me ask you, can I ask you, what is the absolute deadline of task number 1? Is that question valid or invalid? Let me give you a hint. Now, which of the two questions is valid? What is the absolute deadline of task number 1? Now, the second question is, what is the absolute deadline of job number 1 of task number 1? Which of these two questions are valid? Will the absolute deadline of job number 1 and job number 2 of task number 1 will be the same? You guys can listen to me clearly?
No. For absolute deadline, no.
What do you mean by no?
For task 1 and task 2, it will not have.
I didn't say task 1 and task 2. I said job number 1 and job number 2. Remember, tasks and jobs are different. You need to be able to differentiate which one is which. We defined that already all the way in the beginning, the first slide of today's lecture. If you cannot differentiate that, then you will be a lot of problem in discussion. What is task? What is job? I repeat, okay? If I say our task is to read the sensor value every 5 seconds. So that is the task. Okay? The fact that you do reading every 5 seconds, okay? At time 0, you read. At time 5, you read. At time 10, you read. So at time 0, that is job number 1 of that task. At time 5, that is job number 2 of the same task. At time 10, that is job number 3 of the same task. Okay, so that's why I'm telling you guys here, absolute deadline is actually based on each job. Because logically, if this is time equal to 0, you start running your first job here. This will be the absolute deadline of the first job. The second job absolute deadline will be somewhere here. Okay, which is on the next period. If this is 5, so there's another 5 here. So the absolute deadline of job number 2 of the same task will be 10. The absolute deadline of job number 1 of task number 1 will be 5. However, the relative deadline is the same, which is the value of the period. P is equal to capital D. So relative deadline is denoted by capital D. Absolute deadline is denoted by small d. Okay? I'm just telling you notation. Guys, okay tak ni? Is the phase value. Phase of task I is the release time, R sub I, of the first job in the task. Okay, the release time of the first job. Okay, kalau macam contoh yang ni tadi, the release time is 20 of the first job, not 0. Kan? Contoh lah. Okay, so this is the release time of the first job, denoted by the symbol phi. Okay, period, well, very straightforward. P sub I of task, of particular task. And then execution time, also we discussed about it already. And then the relative deadline, which is in most cases will be equal to period unless mentioned otherwise. Now, the hyperperiod offset of period tasks is the least common multiple of their periods. Okay. Hyperperiod is defined as LCM, least common multiple. Dalam bahasa Melayu kita panggil apa ni? Jadi satu lagi, GCD, greatest common divisor, ni least common multiple. Pembahagi sepunya terkecil. Okay, I think you guys learned about this in high school, Form 3, tak silap saya. Okay, the time after which the pattern of a job release execution time starts to repeat. Okay, so that is what meant by LCM here. What is meant by hyperperiod. To calculate hyperperiod, you have to calculate the LCM of the period of all tasks in the particular set given. All right. Ini just throwing formula to you guys. Another important terminology is what we call utilization. What is utilization logically? Basically, how much a particular task uses the CPU. Okay. Utilization is E sub I over P sub I. Okay. Simple. Kalau execution time dia 2, period dia 4, means it's using the CPU 50% of the time. The other 50%, the CPU is free. Okay. What about the total utilization? Well, you just sum up the utilization of each task inside the system. So let's say this is T1, then you have T2, the utilization is 1/8, for example. So whatever that percentage is, you have to add up with this one, so you get capital U. Okay, total utilization. Okay, I mentioned this earlier. Relative deadline is equal to period. Now, all this thing is illustrating the same thing with some visuals. You guys can read them by yourself. All right. The same thing I've discussed earlier, but with slightly more visual. Videos saya pun ada, you guys can watch them. Maybe some of you already watched them. Okay. Before I end this part, any question? I want to go into the next part. It's already 10:50, almost 1 hour spent here. Kalau tak ada, I want to go to the next one. All right, static scheduling. Okay, now we are talking about scheduler. What scheduler we are talking about here? Well, it's about this particular scheduler. Again, let me draw back our bubble from modern operating system. You remember in MOS, we have 3 different schedulers. But here we are talking about only one, which is the scheduler that will decide who inside the ready state will go into the running state. Okay. In other words, who gets the CPU next? Okay. So we'll discuss a few algorithms specific for real-time scheduling algorithm. Okay. Not for general purpose operating system, but real-time operating system. Now, static scheduler is the most basic scheduler. Is a common in real-time system. The desired features in real time, one is predictable and second is simple, because things are very critical, and if it fails, it becomes very bad. Okay, so we want something straightforward. We don't like things which is complex, unnecessarily complex. We try to avoid them. So static scheduler is the most simple scheduler. So let's look at it. So properties of static scheduler. Schedules are stored in a timetable. Okay, the small t is the scheduling time, decision time, and the capital T is either a job or a whole starting at time equal to t. Whole means nothing run at that time, right? The CPU is free. Okay. Refresh system utilization must be E sub I equal to P sub I, and logically, of course, U must be greater than 1. Sorry, U must be less than 1. If it's greater than 1, then we say the system is not feasible. Logically, why is that? Because it's greater than 1 means it's more than 100% usage of CPU, which is illogical for single processor. And note that our discussion is always on single processor, unless mentioned otherwise in any specific case. Okay. Now look at this particular example here. Consider the following set of tasks. We have 3 tasks. Period is given, execution time is given, and relative deadline is also given. Utilization example. So how do we calculate U? Well, we take E over P, right? 1 over 3, 1 over 4, 2 over 10. So the value is 0.783. So that's the total utilization, meaning 78%, 78.33% of the time, the CPU is being utilized by either one of these 3 tasks. Okay. Now, when the timer expires at a particular scheduling point, which is at time equal to t, okay, a job from task so and so is dispatched to the CPU. Okay, so look at this particular table here, pre-computed. Give yourself 1 minute to look at the table so that you have some questions in your mind. So if you look at this particular table right here, pakai color apa nak bagi terang ke sini. Okay, this is simply a counter. This is the time, and this is which particular job of a particular task is being executed at those time. Okay. Now the system creates all the tasks that are to be executed, allocates sufficient memory for the code and data, and brings the code executed by the task into memory. Schedule sets the hardware timer to interrupt at decision time t sub k. On receipt of an interrupt at time t sub k, the scheduler set the timer interrupt to the next interrupt point. And well, this one, if an aperiodic job is waiting, in our case, we don't have any aperiodic job. And then otherwise, we start the next job, task T. All right. So let's focus on our job. Earlier we have 3 tasks. Remember, task 1, task 2, task 3. Their value is like this. Okay, execution time 1, execution time 1, execution time 2. The period is 3, 4, and 10. Now, at time equal to 0, looking at the table, the system decide, okay, we run task number 1. So, of course, this is job number 1 of task number 1. Okay. And then this one is, we run task number. How long does it run? This is 1 unit of time. Remember, here is 0, next is 1. So the first job of task number 1 runs for 1 second. And that's all it needs, which is 1 second saja. Okay, we assume the unit is second. So then at time equal to 1, the CPU is free. So the scheduler comes in and say, okay, now let us run task number 3. Okay, task number 3, it needs how many? 2 seconds, right? However, here we say job number 1. Job number 1 of task number 3. Okay. And then task 2 and so on. Now, if you look at this one, the next ticking is at time equal to 2. However, the one running is task 3. Hey, where is our table? Bukanlah. It's not the following set of tasks. Tak ada yang kat sini lah. There are 4 tasks too. Oh, sorry. These are the tasks. Okay. Sian korang. Okay, we have 4 tasks. Task 1, period 4, execution time 1. Period 5, 20. Anyone has any question here? I'm expecting question from you guys. Because earlier I tell you, we denote T sub X by, first is the phase value, second is the period, followed by execution time, and then capital D. But now I'm only giving you guys 2. Why is that? Because we always assume P equal to D, so we drop D. And we always assume phase value equal to 0 unless mentioned otherwise. So leaving with P and E. All right? Diam ni korang ni. Am I talking to myself? Oops. I didn't see anyone here. All right. Orang ni respon lah sikit. Mengajar online ni betul-betul membosankan. All right, so at time equal to 0, we run T1. It needs 1 unit of time. And then at time equal to 1, we say, let me run T3. Okay? And then at time equal to 2, I say, let me run T2, which is 1.8. So next is at time equal to 3.8. Why do I have I here? Idle. Okay, so at time equal to 3.8, until time equal to 4, the CPU is idle. So at time equal to 4, again, I run T1. Okay, now, how do I finally get into this particular order? Deciding who runs next. Any formula or something? The answer is, for static scheduling, there is no formula. You just arrange the way you like it, as long as all the jobs meet their deadlines. So we prepare this table beforehand. Okay, once the table is ready, we check everything. Okay, all the jobs meet their deadline based on this table. And then we program this table inside. So it becomes like a lookup table. the scheduler will always refer to this table. At time equal to 0, you look at the table. Okay, I run T1. And then later at time, the timer interrupt at time equal to 1. Okay, I run T3 like that. The sequence will be like here, below here. Okay. And here's the calculation for hyperperiod using LCM. I won't teach you how to use LCM. I think you guys learned this in your tingkatan 3 already. Okay, if you guys forgot, you can always refresh back. Banyak online tutorial pun ada. Very simple calculation. Okay, of the period of your task 4, 5, 20, and 20. Then it will gives you 20 as the least common multiple. Pembahagi sepunya terbesar. Least common. Bukan least common, pembahagi pendarab sepunya terkecil. Least common multiple, ya. Okay, we can construct arbitrary static schedule to meet all the deadlines. So that's the thing. So very simple, you just arrange the way you like it. In this case, it arranged like this. Can we arrange them differently? For example, I want to switch this to, can or not? Boleh tak? Yes or no?
Yes.
Anyway, right? As long as you make sure that they meet their deadlines. So that is static schedule. It's highly predictable because we already pre-compute the table beforehand. So it's very good for real-time system. Okay, now translating the table into an algorithm, it becomes like this. So this is the algorithm that you will program inside your computer later on. All right. Now input, store the schedule. So this is the schedule. Okay, so you have a pointer pointing to the first location and then the next location and so on every time the interrupt happens. I equal to 0, a table equal to k to 0. And then we move the timer to expire at the next interrupt point, which is the next scheduling point. Okay, and then we do forever looping here. You just wait for timer interrupt. Once the interrupt happens, then you execute the corresponding job. Then you increment your counter and so on. What about this one? Why doing this? K equal to I mod n. What is this? Any guess? Look at this one. Our tables ends at where? At the hyper period. See, when you prepare a table for static schedule, you must prepare the table until the hyper period, which is 20 in this case. So this table finishes at time equal to 20. So after time equal to 20, we have to again go back to time equal to 0. So this pattern will repeat every 20 unit of time of the hyper period. So that's why we do that. K equal to I mod n. Okay. So your I value will always be either from 1 to 20. Okay. Any, you can watch my video. I think, again, a graphical illustration of what happens. All right. Any question about static schedule? I want to go into the next one.
Time tadi kita set ke berapa lama period dia?
Idle tu.
Betul, sebab idle yang pertama saya tengok 0.2 second and then the next one is 1 second.
Okay, thanks for your question. Now, reality is, when do we get idle? In this case, if you look at the execution time of this guy, right? T2 is 1.8. So that's why in this particular example, maybe it likes to use a simple number. So it lets the 0.2 to be idle. So we only start executing T1 at T equal to 4. But if you decide, well, I want to execute T1 at time equal to 3.8, that's fine. You can remove that idle time. However, in general, in scheduling for real-time system, is a good practice that we spread the idle time throughout the schedule. Like this, no? So you find idle from in the beginning, another somewhere in the middle, somewhere at the end. In hope that at any point in time, if there is any aperiodic jobs, meaning jobs that are not periodic, comes into your system that has to be handled, then we have space for them. Understand? As far as how long the idle time is, well, it very much depends on how much time I have free. In our case, we already calculated 78.33% of the time, my CPU is fully occupied by these 4 tasks. So I only have 22% of the time free for any other jobs or any other aperiodic tasks. So I spread that throughout. Boleh faham, eh?
Betul. Thank you, Doctor.
All right. Thanks for the question anyway. Okay, kalau tak ada soalan lagi, we can go to sekejap, eh. Sekejap. Ya, apa ni? Okay. Next, we're going to talk about another scheduling algorithm, which is known as tick scheduling. You guys are still with me, right? Okay. All right. When we think about static scheduling, right? That we just discussed just now. There is some good thing about it, which of course is highly predictable because the table is prepared beforehand, okay, offline, meaning we prepare the table and then let our computer refer to the table to schedule the task. So it's very predictable. It will be very fixed to whatever we have put inside the table. Okay. However, the bad side of it is it's not flexible. In case we need to add new job or new task, so you need to add new task into the system, then what happened, we have to basically do everything all back from the beginning. We cannot simply just insert the task like that. Okay, I mean periodic task. Apart from that, in static scheduling, if you refer to the current slide right here, it says we need to update the timer expiration time at each scheduling point. So the timer expires time is not the same. Okay, it keeps on changing based on the schedule that we set. So those are the drawbacks of static scheduling. All right. Now, to have a better, not better, but to counter the drawbacks of static scheduling, people introduce the concept of tick scheduling. All right, tick scheduling. In tick scheduling, it says we basically fix the interrupt period. For example, we say every 1 second or every 1 millisecond, depends on whatever unit of time that you're using in your computer system. All right, so we say every 1 millisecond, I'll set my interrupt to expire. So at time 0, we run a particular job. At time equal 1 millisecond, I again send an interrupt signal, and then my scheduler will comes in and look inside the ready state. If there is any job ready for execution, okay, then I will execute those like that at every 1 milliseconds. So that's what we do in tick scheduling. And of course, that amount of time is depends. We decide 1 millisecond or 2 milliseconds or whatever that is, the amount of tick, right? So it becomes like this, yeah. So our timer is where time equal to 0, time equal to 1. But there will be times when your timer expires, then you see inside your ready state, for example, here at time equal to 2, there is none ready. So then there's no jobs to be executed. Okay. And then when it comes time equal to 3, then only you saw T2 is there, ready for execution and so on. All right. Now, so there is also some drawback in tick scheduling. It gives some benefit of flexibility, but then there is a waste of there is an overhead, okay, of ticking our timer at a higher frequency, which involves context switching, okay, which in some cases is a waste of time. Okay, now compared to the completely static schedule, in tick scheduling, a ready task might not be scheduled as soon as it becomes ready because of the tick latency. Understand, right? For example, like here, let's say our tick value is 2 milliseconds. Here the example is 1. Let's say T3 is there already at time equal to 1. However, the timer haven't expired. The timer only comes in at time equal to 2. So task number 3 waited for 1 second for nothing. It was ready, but since the scheduler doesn't comes in and check if anyone is ready because the timer doesn't expire, so there is uh, a delay of task 3 executing for nothing, right? Just simply the way we program it. So that's not good. Now the task must then wait for the timer to trigger the tick at the next scheduling point. And this can cause a delay of, for example, 1 millisecond in the worst case. Now, instead of blindly looking at the clock for determining scheduling points, time sharing is a way of creating a more flexible system. Do you guys remember what is time sharing? The 4 category of operating system. Anyone remember? Time sharing. What is a time sharing operating system? Time sharing means dividing the CPU time into small pieces and giving one piece of to each task. Chronicle the response. Okay, another scheduling algorithm, we call it round robin scheduling. Do I want to discuss this now? I think you guys are familiar with round robin, right? From last semester. Basically, in round robin, basically it's like FIFO also, right? I mean, you can see this video explaining, but basically it's like FIFO that each job is given a time slice. I know you guys are familiar about this. Your final exam question last semester also talked about round robin, right? So a time slice, we call it time quantum. Okay, meaning the OS fixed an amount of time that the jobs will get at every time they enter the CPU. I mean, they get the CPU. For example, 4 seconds maximum. So if any of the job needs more than 4 seconds, then it will be forced to go back into the ready queue and waited for the next turn to finish up whatever it has not finished up in the first iteration. All right. Different from that, we also have weighted round robin. Okay, weighted round robin is slightly different from round robin in a way that different jobs will get different time slice. Okay, meaning the OS gives some priority to certain tasks. Tasks with higher priority will get higher weight, meaning higher time quantum. Jobs with lower priority will get lower time quantum. Okay. Okay, that's about it about this one. I think I'm done with this. Okay, so to recap for today's material, what we have had discussed today, first we talked about one, we talked about modeling a real-time task. Okay, there are a few terms that we talk about. And then we also talk about T denoted by blah, 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 blah. All right. The different notations. So make sure you know those, right? And then we talk about static scheduling, which is very predictable. Or another word for it, we call it deterministic, which means the same. Okay, a real-time system has to be very deterministic. And the third one we talk about tick scheduling. Okay, round robin, you can take them as knowledge. These are the real-time algorithms that we talk about so far. Round robin is also used in real time, but not that fast. Okay, any questions so far? I'm done for today. Later I will release the lab session for you guys? I think I will let you guys choose. Okay, maybe I'll share a Google Sheet or something for you to fill up. So for this week, we will have a physical lab. Let me see. Our lab is what? MKM berapa 3 kan? Anyone check already?
Yes, doctor.
MKM 3 eh? Okay, you guys need to bring your own laptop with Linux inside, okay? Because that lab basically has nothing inside. In fact, that's my preference. You use your own machine because you need to work after the lab also for your lab.
Okay, doctor.
Okay, kalau tak ada apa, I think that's all for today. See you guys next week. Nope, see you guys in the lab. Assalamualaikum and very good.